everyone, and welcome to my first video for my series on calculus. For this video, I just quickly want to give a quick overview of this series and kind of the format of how everything is going to be done, what we're going to go over, how we are going to structure the videos, and kind of an overview. You might have realized that this is my first series on this channel. This is something I've wanted to do for a long time, kind of create like a series of the stuff that I've studied and that I plan to study in the future, and kind of journal everything and have a vault where I can just put all these videos where I talk about the things which I learn. And I just want to get this out of the way right now. Okay, I am not a genius by any means. I am not certified to be a teacher or anything. I think a lot of the times in college when I was struggling with a concept or a problem, the thing that really helped me the most was kind of hearing other people's perspectives on it. And those people didn't necessarily have to be my professor or some, some genius. It could have just been one of my peers, one of my classmates. I asked them about a problem and they kind of give me their interpretation of that problem, or I asked them about a concept and they kind of walked me through it. At the end of the day, I think that is my approach with this series. I really just want to come on here and document any findings that I might have, anything that I might think would help others understand certain topics. And if you get something from that, that's great. Use it to further your academic journey. But if you don't be so discouraged, okay? I'm not gonna be here and claim that I'm the end all be all knowledge source of calculus. There's dozens of resources out there that can help you understand this subject. And if I'm not able to help, that doesn't necessarily mean that others can't help. There are a lot of people out there who make great content centered around this stuff. As for what I'm actually going to be going over for this course, I want it to be really in depth. I'm not going to be just doing a bunch of problems that I find in some textbook and giving the solutions to them. Although that is part of what I will be doing, I really do want to give good videos about the core concepts that are used and the fundamentals that you need to know in order to solve problems that you might see in your class or that you might see in the real world. So I really do want to go as in-depth as possible, and that includes being relatively mathematically rigorous. Now, that being said, I know a lot of you on here, you're just STEM majors, but you may or may not be math majors. And if you're not math majors, then you might not really be that interested in knowing the mathematical proof for everything, which, makes sense. You don't need to know it for your tests. You don't really need to know it in order to be successful in whatever field you're going to. However, I do feel that you can never know too much math, because at the end of the day, that really is what everything in terms of STEM is really built upon, math. And the more of it that you know, the better. So I will be going over some of the proofs for those that may be interested, or for those math majors who you will need to know the proofs. Now, of course, I am going to keep the more math rigorous videos separate from the more necessary videos. That way, if you're not interested in those videos, you can kind of skip over them. Though again, I do encourage you to watch them, even if you don't take notes, just to satisfy your curiosity about how mathematicians are able to be so precise and so exact in their definitions, and so, confident that these laws are able to hold in any circumstance. Now, for the next couple of videos, I am going to be going over some basic stuff that we need to know in order to get to calculus. But this isn't really going to be anything in depth. It's just going to be like a brief whirlwind review of like functions and how we can use them to model certain scenarios. With that being said, I do, expect you guys have some prerequisite knowledge about math, about algebra and trigonometry. You don't need to know too much math in order to really get into calculus. You can just know the stuff that you learned in your pre-calc classes and really any of your classes throughout your high school career. And all right, I think I've talked for long enough. I promise that the intro isn't always going to be that long. It's time we finally start to get into the math. Up to now, the math that you studied from first grade to high school, whatever, it's been pretty static. And what I mean by that is you make a lot of assumptions where in a problem you might have a rate of change, but that rate of change is constant. Maybe you do have problems which are more dynamic than that, but you don't really have the tools equipped to fully analyze those problems. I'm going to kind of go a bit deeper into what I really mean here. Let's say we have some function that is describing the distance that an object is from our origin as we throw it up in the air. All right? This is a trajectory that our object goes. This is our y-axis, which is measured in meters. This is our x-axis, which is measured in time. And this is just, simple graph. Distance versus time. This is a very simple graph that I've drawn here, but it's not very useful in the sense that when we throw objects in reality, they don't just fly straight without falling at this constant speed. But in this example, that is exactly what we see. And the reason why I modeled it this way isn't because it's realistic, but because it's easy to kind of understand this mathematically. We have some change in the x-axis, which is the time that elapses, and we have some change in the y-axis, which is the distance that the ball goes through in that time interval. So we usually call this delta y and delta x, and hopefully you guys can recall what a slope is. A slope is pretty much the change in our function divided by the change in our independent variable. And in this case, the slope actually has a physical meaning. If you've ever taken a class in physics, you'll know this. If you haven't, don't be too disappointed by that. I don't really expect you guys to know this, but I'm telling you this now. The slope of this graph is going to be equal to the speed of our object. Hopefully you guys can intuitively see why the slope in this case is a representation of the speed that our object is going. We see here we have some change in y. That is pretty much how far the ball goes. And then that change in y is occurring over a certain time interval. So this delta x is telling us this is how long it takes. Delta x is how long it takes for the object to travel this certain distance. That is our exact description of what speed is. The speed of an object is how long a distance, how far an object goes within a certain time interval. Sorry, I misspoke. Anyways, hopefully you guys get that. But again, this is mathematically simple for us. We know how to calculate the slope. We know what these values are. We can easily calculate this. But it's not realistic. I'm going to draw a more realistic example of what we might see if we throw a ball up in the air. When we throw a ball up in the air, it's constantly falling. At least that is when we throw it while we're on the surface of the earth, which we're going to assume that that's what we're doing. So it doesn't go in a straight line. It follows kind of this parabolic path. It is going higher and higher in this first interval. Then it kind of stops in the middle here and it starts falling back down. How would we mathematically analyze a function like this? Say we want to use a slope, all right? We want to use a slope to see how fast this ball is going. Well, the problem is that the slope is going to have different values for different intervals. In this last case, the slope was the same no matter which y value or x value we chose to measure the slope at. It's always going to be the same. But here, it's going to be different. If we wanted to, for example, measure what the slope would be from these 2 points, slope for this, it would look like something like that. All right, this is our slope. And again, it is a mathematical description of how fast the ball is going. But in this case, the slope doesn't represent the instantaneous speed of the ball. What do I mean by the instantaneous speed? Instantaneous speed is how fast a certain object is going at a moment in time. If we were able to freeze the ball along its trajectory and look at it at one instant in time, we could say, in this moment, the ball is going this fast. We cannot use this calculation to say that. We cannot use this slope to say that. This slope right here is not a representation of the instantaneous speed. This slope is a representation of the average speed. All right? And if you don't necessarily understand that fully in this moment, that's okay. This is a physics problem. So if you've never taken a course on physics, this is probably a little bit confusing. This slope is not a good representation of how fast the ball is going at an instant moment in time. We need something else. The problem that I just brought up, it's related to change. Here, we have a change in delta y over delta x. But what we want to do is find a better representation of change than the simple slope that we've developed up till now. And the thing that we're going to use to solve this problem is a concept I'm going to talk about in a couple of videos. Is called the tangent. The second big problem in calculus is the problem of the area under a graph. And you might be wondering, well, why does area matter to us? Why do we want to solve for the area? Again, I'm going to use a physics example for this. The area under this graph, this is the same graph that we had as before. It's some object that is going straight. It's following a straight path after we throw it in the air. The area under this graph, it's not just some mathematical property that we can calculate. It represents a physical quantity. It represents that the distance that the ball has traveled up till this point, from the moment that we have thrown the ball from the origin at t equals 0 up till this moment that we can define arbitrarily, the area from here until here of this graph is the distance that the ball has traveled. Again though, this is a simple thing to calculate in this case because this is just a triangle. We know how to calculate the area of a triangle, all right? We've already established though that this graph isn't a very realistic representation of what we might see. This is a much more realistic representation. However, how will we calculate the area under this graph? If I wanted to find out how far the ball traveled up till this point from the moment that it's thrown, I would need to find the area under this graph. This is not a perfect triangle. You can see there is a slight curved path here. All we can really do right now with the knowledge that we have is estimate the area. Yeah, it kind of looks like a triangle. Maybe we could get away if we kind of drew a line from this point to this point and just calculated the area of that and say, okay, this isn't the exact area. It's a slightly larger area than what we calculated, but it's pretty good. But let's be honest, we want to be as exact as possible. And an approximation like that. Although it might be enough in some cases, it's not going to be enough in all cases. We went over two problems, the problem of the area and the problem of the rate of change. These two might seem mutually exclusive, but they're actually intrinsically related. And in fact, their relation is so fundamental to calculus that it's literally called the fundamental theorem of calculus. And once we have developed enough understanding of both of these problems, we will be able to connect them, and that's when we can really start to do some amazing things. All right, I think that's going to be it for this video. Again, I just wanted this to be a very quick overview. I don't really expect you guys to have learned too much just yet. The next couple of videos, as I mentioned before, are going to be a brief refresher on functions and how we can use them to model stuff. I'm sure you've realized by now the amount of cuts that have been in this video. I'm still very new to this. I stumble a lot over my words. I struggle a lot to really get out the right thing to say. I hope that I will get better over time. If you guys have any feedback of anything that I did on this video, please let me know. I really do need it. I'm still very new to this. I've never really talked to a camera before. I've never really done anything like this before. It takes me so long to say the right thing, but hopefully I will get better over time. Until then, be honest. Let me know what you guys think, and let me know if there's anything you think that I could improve on. With that being said, I will see you guys in the next one.